Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a paper that's been making waves. Vision language models are blind. It's a provocative title, right?
Provocative is an understatement. We've seen these models do some pretty amazing things. Image captioning, visual question answering. Blind seems harsh.
But is it? I think the paper hits on something fundamental. Are these models actually understanding what they're seeing, or are they just incredibly sophisticated pattern matching machines?
Exactly. I think this gets to the heart of it. Blind might be a strong word for a headline, but I'm betting their actual results show that these models fundamentally fail when it comes to abstracting and understanding underlying spatial relationships.
So, for our listeners who might not be completely up to speed, what are vision language models? And what kind of tasks are they typically used for?
Think of them as AI systems that can see and talk. They take an image as input and generate a textual description or answer questions about the image. They're used in all sorts of applications, from helping visually impaired people navigate the world to automatically tagging images on social media.
Yeah, and they're getting integrated into all sorts of things. Self-driving cars use them to identify objects in the road. Medical imaging uses them to detect anomalies. The applications are vast.
But that's exactly why this paper is so important. If these models are, in essence, blind to certain aspects of visual information, it could have serious consequences in those real-world applications. Imagine a self-driving car misinterpreting a complex intersection because it doesn't truly understand spatial relationships.
Okay, that's a fair point. So, what specific limitations did the paper highlight? What makes them say these models are blind?
Well, they tested the models on tasks that required more than just recognizing objects. They focused on things like understanding spatial relationships, reasoning about the physical properties of objects, and inferring common sense knowledge from a scene. They found that the models often failed in surprising ways.
Right? They gave examples where the models would misinterpret the orientation of objects or fail to understand how objects would interact with each other. It's not just about seeing a table and a chair. It's about understanding how those objects relate to each other in 3D space and what that implies about the scene.
Give me an example because I'm still struggling with this. I've seen these things generate pretty accurate captions. It's not like they're completely clueless.
Okay, imagine a picture of a dog standing behind a fence, partially obscured. A vision language model might correctly identify the dog in the fence. But if you ask it, is the dog inside the fence enclosure? It might get it wrong because it's not truly understanding the spatial relationship. It's just recognizing the objects and spitting out a statistically likely answer based on its training data.
Okay, I see. It's not about object recognition, it's about spatial reasoning and understanding the relationships between those objects.
Exactly. The paper makes the point that current models are very good at identifying visual features and associating them with words, but they lack a deeper understanding of the underlying scene geometry and physics.
It's like they're memorizing the training data, but not actually learning the underlying principles. Think of it like teaching a parrot to recite Shakespeare. It can say the words perfectly, but it doesn't understand the meaning behind them.
Right, and this is where I think the coordinate system issue comes in. Current models are primarily trained on pixel data, which is just one coordinate system. They struggle to translate that into other representations, like a 3D scene graph or a symbolic representation of the spatial relationships.
So they're saying these models are essentially pixel blind. They can see the pixels, but they can't see the underlying geometry.
Pretty much. They're good at recognizing patterns in pixels, but they're not good at inferring the 3D structure of the scene or reasoning about how objects would behave in that scene.
And this highlights a major limitation of the current deep learning paradigm. It's all about pattern matching and statistical correlations, but it doesn't provide a way to represent and reason about symbolic knowledge.
But isn't that what deep learning is supposed to be doing? Learning these underlying representations automatically from data?
In theory, yes, but in practice, it seems like it's getting stuck at a relatively superficial level of understanding. It's learning to correlate pixels with words, but it's not learning the underlying rules of geometry and physics.
That's why I found the alpha geometry 2 examples so fascinating. It shows that a different approach, one that incorporates more explicit geometric reasoning, can achieve impressive results.
Okay, remind our listeners about alpha geometry 2. What is it and why is it relevant here?
Alpha Geometry 2 is an AI system developed by Google DeepMind that can solve complex geometry problems at a near-human level. It's significant because it combines deep learning with symbolic reasoning techniques.
Crucially, it doesn't just brute force its way through possible solutions. It actually understands the geometric principles and uses them to deduce the correct answer.
Exactly. It's like it has a built-in understanding of geometric axioms and theorems, which allows it to reason about the problem in a much more efficient way than a purely data-driven approach.
So it's not just recognizing patterns, it's actually understanding the underlying mathematical rules.
That's the key. It's a neuro-symbolic approach. It combines the pattern matching capabilities of deep learning with the reasoning capabilities of symbolic AI.
And I think that's the direction we need to go in if we want to overcome the limitations highlighted in the vision language models, our blind paper. We need to find ways to integrate symbolic reasoning and geometric understanding into our AI systems.
Yes, the gold medal performance of such algorithms offers a glimpse into how to marry the strengths of computational power with biological understanding. And I hope that in the future we can use insights from neuroscience to drive algorithm design.
But how do you even do that? How do you combine these two fundamentally different approaches?
That's the million-dollar question. There are a few different approaches being explored. One is to use deep learning to learn symbolic representations of the world. Another is to use symbolic reasoning to guide the training of deep learning models.
I think the key is finding a way to translate between these two representations seamlessly. We need a system that can take in raw sensory data, like pixels, and convert it into a symbolic representation that can be used for reasoning and planning.
And I think that's where neuroscience can play a crucial role. By studying how the brain processes visual information, we can gain insights into how to build more intelligent AI systems.
So, you're saying we should try to reverse engineer the visual cortex.
Not necessarily reverse engineer, but definitely draw inspiration from it. The brain has evolved over millions of years to solve these problems, so it makes sense to look to it for inspiration.
Absolutely. The brain is incredibly efficient at translating between different coordinate systems and reasoning about spatial relationships. If we can understand how it does that, we can build much more powerful AI systems.
One thought I've had related to the paper is how can we bridge the gap between the abstract mathematical operations performed by current vision language models and the concrete, spatiotemporal processing occurring in the visual cortex. Perhaps analyzing the neurophysiological mechanisms in the brain can reveal novel representations and algorithms for integrating vision and language that go beyond the current brute force deep learning methods.
But even if we do figure out how to combine deep learning and symbolic reasoning, will it be enough to achieve true AGI? Or are we still missing something fundamental?
That's the big unknown. I think we're still a long way from achieving true AGI. But I do think that by focusing on building more sophisticated neurosymbolic algorithms, we can make significant progress.
I agree. I think the current deep learning paradigm has hit a wall. We need to start exploring new approaches that incorporate more explicit reasoning and knowledge representation.
And I think that the vision language models, our blind paper, is a wake-up call. It highlights the limitations of current AI systems and points us towards a more promising direction for future research.
Okay, so what specific research directions should we be pursuing based on this paper? What are the next steps?
From my perspective, we need to focus on developing better neurosymbolic algorithms. Algorithms that can learn relational structures and symbolic knowledge about the world as opposed to just pattern recognition. What are the necessary steps to develop algorithms that can link perceptions with abstract concepts and logic?
I still think deep learning has a lot to offer. I think we need to figure out how to embed our understanding of visual context within deep learning architectures. How might we do that without significantly increasing the required data? Perhaps we need to explore different architectures or training methods.
I think we need to focus on the coordinate system problem. We need to develop a more fundamental understanding of spatiotemporal relations, which could pave the way for constructing an AGI with a deeper conceptual model of the world than is currently possible with deep learning alone. We need something akin to a fundamental mathematical framework for spatiotemporal reasoning.
I agree with all of that. And I would add that we need to look more closely at the brain. We need to analyze the neural mechanisms that drive geometric reasoning in humans and integrate those findings into the development of algorithms. Such a combined approach could lead to more robust and adaptable AI capable of understanding spatial relations in a way that rivals or surpasses human abilities.
What about the issue of data? Do we just need more data, or is it a matter of the quality of the data?
I think it's both. More data is always helpful, but we also need data that's specifically designed to test the reasoning abilities of these models. We need to create data sets that force them to go beyond simple pattern matching and actually reason about the world.
And we need data that's representative of the real world. Current data sets are often biased and don't reflect the full complexity of the visual environment.
Yes. Also, maybe further research should focus on understanding the internal representations used by alpha geometry, too, and then compare it to similar representations employed by humans. Neuroimaging data on geometric problem solving might provide clues about how to engineer similar internal models and algorithms.
So, we're talking about creating more challenging data sets, developing new algorithms, and drawing inspiration from the brain. And that's a pretty ambitious research agenda.
It is, but I think it's necessary if we want to build AI systems that truly understand the world around them.
Agreed. The vision language models are blind paper has opened my eyes to the limitations of the current approach. It's time to start exploring new possibilities.
I think also the limitations discussed in the paper give me hope that a future of biologically inspired AI systems that utilize neural mechanisms is on the horizon, so it is not all bad.
One question that keeps nagging me, though, is the generalizability of alpha geometry to success. If the model excels at geometry, how transferable are the underlying techniques to other problem-solving domains, for example, physics or complex engineering designs? This should be a critical part of any future studies to understand if it is just solving a particular problem or a more complex problem in a deeper sense.
That's a valid concern. The success in geometry might be due to the well-defined rules and axioms of the domain. It's not clear how well these techniques would generalize to more ambiguous and complex real-world problems.
And that gets back to the coordinate system issue. Geometry has a relatively limited set of coordinate systems. The real world is much more complex and requires a much more flexible and adaptable system for representing spatial relationships.
Exactly. That also makes me wonder, how does alpha geometry leverage the principles of visual spatial reasoning, as understood from neuroscience, to solve geometric problems? Analyzing the neural correlates of geometric intuition in humans could illuminate design principles for improved AI performance.
Another thing I'm curious about is how alpha geometry 2 handles different coordinate systems, Cartesian, polar, etc. If it can seamlessly translate between these systems, this hints at a sophisticated ability to represent and manipulate geometric concepts, which seems crucial for truly understanding spatial relationships. Is there evidence of a form of intrinsic geometrical understanding, or is it simply relying on massive amounts of data?
And how does it handle uncertainty? Real-world data is noisy and imperfect. Geometry problems are typically clean and well-defined. How would alpha geometry 2 perform in a more realistic setting?
Those are all excellent questions. I suspect that alpha geometry 2, while impressive, is still limited in its ability to generalize to more complex and ambiguous real-world problems. But it's a step in the right direction.
I agree. I see it as a proof of concept that neuro-symbolic approaches can be effective. Now we need to figure out how to scale up these techniques and apply them to a wider range of problems.
And maybe we need to rethink our evaluation metrics. The vision language models or blind paper shows that current metrics can be misleading. We need to develop metrics that are more sensitive to the reasoning abilities of these models.
Yes, the reliance on a gold medal suggests a clear, explicit evaluation metric, like we saw with alpha geometry 2. How could we apply more robust, symbolic evaluation methods to complex systems instead of relying solely on metrics that might be susceptible to hidden biases in the data?
I think that's a crucial point. We need to move beyond simple accuracy metrics and start evaluating these models on their ability to generalize, reason, and adapt to new situations.
And we need to be aware of the potential biases in our datasets and evaluation metrics. AI systems are only as good as the data they're trained on, so it's important to ensure that the data is representative and unbiased.
Okay, so to summarize, we've identified several key areas for future research: developing better neuro-symbolic algorithms, improving our understanding of spatiotemporal reasoning, drawing inspiration from the brain, creating more challenging datasets, and developing more robust evaluation metrics. That's a pretty comprehensive list.
It is, but I think it's a necessary starting point for addressing the limitations highlighted in the vision language models or blind paper.
Agreed. I think we're at a critical juncture in the field of AI. We need to move beyond the current deep learning paradigm and start exploring new approaches that can truly understand the world around them.
I would agree. And I think that by combining the strengths of deep learning, symbolic reasoning, and neuroscience, we can make significant progress towards achieving that goal. The implication of a lack of meaningful understanding of vision in modern models is quite concerning, especially in the context of complex tasks requiring real-world comprehension.
So, if we're all in agreement that current vision language models are, in some sense, blind, what are the implications for the future of AI development?
I think it means we need to be more cautious about deploying these models in safety-critical applications. We need to be aware of their limitations and ensure that they're not making decisions that could have serious consequences.
Absolutely. And it means we need to invest more resources in developing more robust and reliable AI systems. Systems that can truly understand the world and reason about it in a safe and responsible way.
Exactly. If vision language models are so fundamentally limited by their lack of true visual understanding, is the current focus on purely data-driven approaches to AI in danger of producing systems that are impressive in some respects, but ultimately not intelligent? This suggests we may need a paradigm shift towards more biologically informed models that incorporate a richer understanding of spatial and temporal representations.
Well, this has been a fascinating and thought-provoking discussion. I think we've all learned a lot from the vision language models or blind paper and the implications it has for the future of AI.
I agree. It's a reminder that we still have a long way to go before we achieve true AGI, but it also highlights the exciting possibilities that lie ahead.
Absolutely. It's a challenge, but it's also an opportunity to build AI systems that are truly intelligent and beneficial to humanity.
It's been great having you all here and unpacking this important research. Thanks for joining us on Cognitive Spirals.
Thanks for having me. It's always a pleasure.
My pleasure. Thanks for the stimulating conversation.
Thank you. I enjoyed it very much.